Okay, this is lecture 14. So now let's go to the second half of our semester. This is the remaining lecture plan for our second half. So this number is corresponding to the lecture index, 14th lecture. This is today, and we will have more lectures till the end of this semester. And you know that the total number of our entire semester will be 26. L26 will be the last one. However, L25 and L26 will be YouTube lectures due to my business trip to Japan. So offline lecture will end in this day. So maybe June 4th. After that, you will have two more YouTube lectures as usual. And in this case, so these two YouTube lectures are reserved for more advanced topic, not covered in our usual textbook. So you can just watch and learn how can we further investigate the important topics in VLSI devices. So the textbook lectures will end at this lecture 21st. And final lecture, actually this is not my decision, but decided by university. But I guess that maybe our final exam will be this date. So June 16th. So please prepare your final examination. So as usual, the coverage of our final examination will be the entire lecture content we have studied up to now, or up to the end of our entire semester. So please prepare that examination. And yes, this is my tentative plan for remaining lectures. And today is lecture 14, and we will talk about substrate bias and channel mobility. After that, so this is the end of long channel MOSFET discussion. After that, from this Wednesday, we will start the discussion about short channel device. Up to now, we have studied extremely long channel device. For example, if we consider 90 nanometer technology, however, the one we are currently talking about is 1 micrometer long channel, or even longer devices are considered up to now. And after that, we will talk about how can we consider this short channel effect and other effects like velocity saturation, channel length modulation. Yes, you already have seen these topics in your microelectronics course or the junior level semiconductor device physics course, but we will revisit this topic again because we need more advanced treatment on these topics. After that, yes, this is for short channel devices in principle. After that, we will apply some even more advanced topics. How about the MOSFET scaling? So this is, so maybe in lecture 19 and 20 are devoted to the MOSFET scaling, but this is really traditional one. Traditional MOS scaling for planar MOSFET. This is no longer valid to our current state-of-the-art device. However, you will learn a lot about this scaling of MOSFET technology. After that, quantum effect will be discussed. So this is, I think that this is more than 1 hour long lecture content. After that, we will go to the double gate MOSFETs. So as a student living in 2025, I guess that practically, the important one is this double gate structure. Although we are currently talking about planar MOSFETs, but our MOSFETs are no longer planar MOSFETs. they are always should be treated as a double gate MOSFET or even further advanced one. So I guess that this is a very important lecture for state-of-the-art device. After that, lecture 23 and 24 will be devoted to even more advanced device architectures like FinFET and complementary FET, so-called CFET. This is not related with CMOSFET. So you know CMOSFET, and unfortunately CFET is not exactly equal to the CMOSFET, although it is a kind of a CMOSFET. So you will learn what is a CFET and what it will be the future technology. After that, so lecture 25th and 26th will be devoted to even more advanced topic, which will be quite stimulating for your research or study interest. Okay, this is my plan, and let's go to today's lecture. Today's lecture, as I told you before, so devoted to the substrate bias one and channel mobility. Before talking about the substrate bias effect and mobility, first of all, we have to close our discussion about subthreshold slope. So subthreshold slope is quite important concept, and I already emphasized its importance. And subthreshold slope is usually written as S, capital letter S, or sometimes SS, so substrate slope. So this is written in a unit of millivolt per decade. So in order to make 1 decade difference in our current, how much voltage difference should be applied to our MOS system, MOS device, that is given as subthreshold slope. So let's think about this one. 1 volt per decade. What does it mean? So if we have ID as a function of a VGS, if we have a certain device whose subthreshold slope is just 1 volt per decade, means that, let's say that there was a certain value, drain current value, at a certain gate voltage. Let's say this is happen to be V naught and ID naught. And if we have such kind of a very bad subthreshold slope, it means that when we increase our gate voltage by amount of 1 volt, so V naught plus 1 volt, then our current will be just 10 times. So 10 ID naught. So that will be the curve we will have. Of course, here we takes just a logarithmic scale, the semi-logarithmic scale for y-axis. This will be the graph for this 1 volt per decade case. However, this is really a kind of a worst device we can imagine. So more reasonable device has the range like just 0.1 volt per decade. So then please try to draw the same graphs starting from the same starting point here. If our SS, subthreshold slope, is just 0.1 volt per decade, then what will happen? By increasing our gate voltage only by 0.1 volt, we will have 10 times higher drain current. So simply speaking, this will be the graph for our 0.1 volt per decade device, and this is corresponding to 1 volt per decayed device. So which one is a better one and which one is a worse one? Obviously, this one shows much steep transition between off state and on state, and we love to have this a steep slope. And you know, if you have this kind of a device, this is the extremely bad device. You never use it. So please, if you have this kind of a number, it means that in order to have 10 to the 5 times difference between your off current and on current, how much voltage difference is required for your device? At least you need 5 volt difference between your off voltage and on voltage. Otherwise, you never get 10 to the 5 times difference in your drain current. However, if you have just 0.1 volt decayed for your subthreshold slope, then this number will be just reduced to 0.5 volt. So within very small voltage range, you can turn it on and turn it off. So it is corresponding to your ability to reduce VDD value. VDD value can be drastically lowered by this advanced technology with higher or steeper SS value. So if you have reduced VDD value, then you can also reduce power consumption of your device drastically. So that is the main reason why we have to have steep SS value. So the discussion shown here can be quite well skipped, so please have a look at this discussion. This is the expression for your drain current, and basically this is given by exponential something. Something means that gate voltage. If you have increased your gate voltage, then current will be increased exponentially. However, there is a normalizer factor corresponding to M times KBT. So this M actually determines the amount of normalization. If M equal to 1, then you will have a steeper one, and if you have M is much higher than 1, then your slope will be degraded, and eventually the quantity called the substrate slope is given as this ratio. So in a semi-logarithmic graph, so slope between your drain current and gate voltage. So this is a definition of a subthreshold slope, and simply given as this M times something. This something is actually 60 millivolt per decade at 300 Kelvin. That's the reason why we can easily say that subthreshold slope is given as M times 60 millivolt per decade. And when we have M quite close to 1, ideally our SS will be just 60 millivolt per decade. So please have a look at this graph taken from quite a recent IDM. So IDM 2024 is the last IDM we have seen. So by the way, IDM is an international conference where companies are demonstrating their state-of-the-art advancement in the device manufacturing technology. So as you can see here we have a VGS. This is N MOSFET, and this is for P MOSFET. And where can you find the subthreshold slope? So here we have ID written in semi-logarithmic scale, and this subthreshold slope is for subthreshold reason. So here maybe this part is for our subthreshold slope, and you can see that there is a certain slope. So let me just do it together with you. So how can you estimate the sub-threshold slope? It is quite easy. Starting from here, let's say that there is a certain gate voltage to achieve 10 to the minus 7 of your drain current. After that, when we increase it by amount of 10 times, so we will go to 10 to the minus 6. And in order to achieve this 10 to the minus 6, of course, also we have certain, yes, we will have certain gate voltage, and please try to estimate the difference between these two gate voltages. So that is corresponding to here voltage difference to realized 1 decade difference of drain current. This is corresponding to the SS quantity. And as you can see, please have a look at this scale. This is 0.5 and 2 ticks are corresponding to 0.2 volt difference. So now you understand this is corresponding to 0.1 volt difference. And when we have a look at these numbers, although I just made a crude drawing, but you can see that this is corresponding to the difference, and this difference is really corresponding to 0.06 volts to introduce 1 order of magnitude difference in your drain current. So it means that this is the state of the art fabricated by Intel, and now it means that currently our technology really achieve sub-threshold slope quite close to 60 millivolt per decade. And please try to remember your expression about M value. How did you define your M value? If you remember correctly, so M value is corresponding to 1 plus certain ratio. What was the ratio? The ratio was the depletion charge to oxide, depletion capacitance to oxide capacitance. And when you say it is quite close to 1, it means that this second term almost vanishes. This almost vanishing number is corresponding to what? The impact of depletion charge is almost gone. So this is because nowadays our device is no longer planar type, but this is a FinFET or gate-all-around transistor. So let me explain a little bit further about these ones. So in the case of FinFET, we have really the substrate. Yes, so we have to actually consider this depletion capacitance. However, it is virtually or quite close to the fully depleted devices. So in this device, although we can define depletion capacitance, but it is quite small. And in the case of a gate-all-around transistor or nanosheet transistor, actually we don't have any substrate contact. And for this kind of devices, actually the dependency on the depletion charge is almost gone. So that's the reason why for advanced devices we can achieve the M value, which is quite close to number 1. This is really good news for our technology. When you come back to the planar era, even when you have quite good technology, the thing you can achieve from planar MOSFET was at best 90 millivolt per decade or 100. Yes, if we have such kind of number, then everybody at that time will be quite happy about your SS value. However, when we just switch it to the different architecture called as a FinFET, things has changed completely. So nowadays, if you have the numbers like 90 or 100, then maybe, oh, what's wrong? So there is something wrong in our technology. There is something makes our device working worse than expected. So this is really important to change the structure of our device. That is, structural dependency is nowadays a main driving force to make innovations in semiconductor device technology. Okay, so anyway, this is a short discussion about subthreshold slope. So please do your study starting from the subthreshold current expression to this SS expression. So this is quite important. You should be able to derive the expression by yourself. So please. Okay, so now let's go to our main lecture contents, substrate bias. Well, I think that nowadays it is a little bit off the trend because, as I told you before, FinFET has almost no bias dependence, and nanosheet case, actually this is perfectly no impact on substrate bias because there is no substrate at all. However, in the case of a planar MOSFET, this substrate bias has been used quite usefully to control your device. For example, like this. Let's think about a certain chip, although I just draw a square. Let's say that this is a chip, CPU chip, for example, and say that there are many different blocks for inside this chip, and in many cases only a part of your chip is actually activated, and for other parts actually they are just idle. All of us are just in our off state current. But anyway, they should be ready for later use, so they should be connected to the bias conditions. So unfortunately, they should spend standby power, although they are not actually working as a logical circuit, but anyway they are connected to the bias condition, so they are flowing off current. That was the situation, and this is actually happening even nowadays. So one technique they have used, they means that designers have used in this case is when it becomes clear that these parts are not used in a near future, then they apply certain technique to increase the threshold voltage of those devices considerably. So what does it mean? Let's say, let's think about this one. ID versus VGS. In nominal case, let's say that this is the usual threshold voltage of our device, and of course this is written in logarithmic scale, semi-log scale. Then what we can expect is, okay, there is 60 millivolt, or anyway SS, subthreshold slope. After that we will have this kind of turned on behavior, and this is the VDD value. So when we turned off our transistor, what we can expect is, even though we have tried to turn off our device, there will be the leakage current due to the operation of our transistors. And next one is, now assume that we have a certain means. We have no idea how can you do that, but let's assume that we can just shift this threshold voltage toward this positive direction. Let's assume, without changing our structure, by certain means. So magically we can change it to this direction. Then what will happen? If threshold voltage is shifted toward the positive direction, then since this is threshold voltage, below this threshold voltage, we will have just a straight line in this semi-logarithmic scale, and this is corresponding to there will be certain subthreshold slope. Then also we will have a relatively small on current. So if we can make such kind of shift of threshold voltage, what you can expect is, okay, I on is significantly reduced to this smaller value. Well, this is not that good news for operation. And at the same time, also we can see that our leakage current will be reduced significantly by this subthreshold operation. But if we have a certain guarantee that there is no actual device working in this case, it means that we never use this part. So sorry about that. We say we never use this on current. We will always use only this off current condition. Then now you understand, increasing the absolute value of threshold voltage will be always quite a good choice to reduce the leakage current significantly. So are you with me? So let's say that this one has a SS equal to 0.1 volt per decade. So, and let's say you have introduced increase of your threshold voltage 0.2 volt. What does it mean? By increasing your threshold voltage by 0.2 volt with given subthreshold slope, you achieve that your off current is reduced by 100 times. Are you with me? So because threshold voltage is changed by 0.2 volt, and this is 2 times 0.1 volt, and in this subthreshold slope, if we have 0.1 volt difference, leakage current will be reduced to 1 order of magnitude. Since that is repeated twice, we will have 100 times lower leakage current. This is really a big deal to save your off current condition. So simply means that in your chip, if you are not going to use these part in your near future, maybe you can just increase your threshold voltage considerably. Then you can reduce the power consumption of this unused part. Maybe you can ask me this question. Well, then why don't you just completely shut down those parts? So instead of increasing threshold voltage, the even better way is to increase or completely shut down the power supply. Yes, that will be the best way, but point is, if you completely shut down that device, that part, for example, then now, it's time to use this part again. Then we have to the initialization of all kinds of this part again and again. It will take quite a long time to come back to normal operation condition. So in order to avoid such kind of a long waiting time for waking them up, so we use this technique to increase threshold voltage. So now you understand, maybe changing the threshold voltage can be a good way to control power consumption, especially standby power consumption. But how can we actually shift this threshold voltage? Up to now, we have assumed a certain magical way to increase threshold voltage, and that is shown here. So substrate is biased with negative voltage in the case of N MOSFET. So let me just think about this one. So source, drain, and substrate. Up to now, we have always assumed that this is grounded and this is also grounded, and we apply certain voltage VDS, and gate is also VGS. That was the nominal bias condition we have considered up to now. And source and substrate are always tied together. So same bias voltage has been applied to these two terminals, but now we wanted to introduce a different voltage to this one. Here we apply body voltage. So body voltage can be differed from source voltage. There is a certain condition. So please, let's say that we apply 0.1 volt. So then what will happen? Please note that this substrate is p-type, lowly doped p-type, and source is highly doped n-type. So actually there is a p-n junction between source and substrate, and if we apply 0.1 volt to our p-type region, this p-n junction is forward biased. So what does it mean? Now this p-n junction can conduct a certain amount of current, and this is directly connected to the leakage current. This is not a desirable case, so usually we never apply positive bias to our substrate. Instead, if we apply minus 0.1 volt, then what happens? Now still we have a p-n junction, but our p-n junction's anode, this p-type region, is negatively biased, and our p-n junction is now reverse biased. In this case, the amount of leakage current is still negligible, so we will use this bias condition only for our application. So don't be confused. When you have your N MOSFETs, then you must apply 0 or negative value to your p-type substrate. Otherwise, you have additional current conduction between these parasitic p-n junction. So in this case, now you have a non-zero value, like for example 0.1, 0.2, minus 0.1 or minus 0.2. So then what does it mean? It is corresponding to this one. I'm saying that now 0 minus 0.1 volt and 0.7 volt and 0.7 volt, gate, source, drain, and substrate or body. This condition is identical to this case: source, drain, gate, body. now body is biased to 0.0 volt, and now gate is corresponding to 0.8 volt. Yes, and also this is corresponding to 0.1 volt and 0.8 volt. So yes, you know they are identical. Why they are identical? Because between this and that, we just introduce global shift of applied bias voltage. So that's the reason why we expect the same amount of current conduction. So what we have done is, in this case here, we just apply this bias condition. So I guess that yes. So please have a look at these ones. This expression is obtained from our previous expression. However, we have assumed that this dV over d phi s is equal to 1. So maybe you remember that at the end of our previous lecture, we have discussed about this relation. So when we go to the subthreshold region, actually this is not valid. However, if we go to the strong inversion region and in a triodal mode, then this is really correctly describing the behavior of our transistor. In this case, we can write down in that way, and just to use these conditions. So instead of VG, yes, now we have a lifted gate voltage, and also the substrate our surface potentials are also changed by minus Vs and also minus Vs. Bias conditions are just changed, and by using these conditions, so you can just follow the expressions shown here. Simply speaking, now let's go to the final answer. You can find that threshold voltage is affected by this part. This part is the same as before, even when the substrate was biased to 0. However, you can see that here certain change. So when Bs substrate is or body is grounded, then of course you don't have this term. Yes, and now when your VVS is now negative 0.1, then what will happen? Instead of this 2 times phi b, now you will have 2 times phi b plus 0.1 volt. The larger value will be entered into this part. Then what you get is, in this case, in this negatively biased substrate case, your threshold voltage will be increased. So please have a look at this example taken from Professor Tower's book. So please note that this numbering is corresponding to his second edition. You can find also third edition and second edition, but this is corresponding to the second edition. And you can see that when body voltage is 0, your threshold voltage happen to be, for example, 0.8 volt. However, when you apply negative bias, so please be careful, although here written as 2, this is not just 2 volt. your substrate is biased with -2 volt. So please, this is corresponding to minus body voltage. In this case, you can see that subthreshold voltage is increased. So the trend is, if you apply so-called, this bias voltage is called as back bias. Why they call it as a back bias is, usually people say that this part, this face is front side, and people say this side is back side, and body in our imagination, so body is connected to this substrate, so we say that this substrate bias as a back bias. But this is just can I say, just for idealized case. In actual case, our bias condition is given as certain tab. Here we have P plus region, and this is a P-type substrate, and by applying certain voltage to our P-type tap region, actually that is the way we actually apply certain bias condition to our P-type substrate. But anyway, this is the practical way. In our imagination, substrate is located in a backside, so this substrate bias is called as back bias. So by increasing back bias, we can increase threshold voltage, and that is corresponding to the way to reduce off-state current and also reduce on current. However, we never use on current. In this case, we just enjoy the reduced off-state current. Okay, so this is how can I say, if you are working with state-of-the-art device, nanosheet MOSFET, unfortunately there is no longer substrate content. So now our transistor is not 4-terminal device, but that is now 3-terminal device. There are only gate, source, and drain, and there is no body at all in our state-of-the-art device. But anyway, although we are currently living in 2025, still there are tons of planar MOSFETs actually fabricating and being used our important circuits. For example, think about your automotive device. Well, I can say, if you buy a car, then it contains a lot of semiconductor chips in it. So do you think that they are made of FinFET or gate-all-around transistor? Actually not. Why? Because their condition, their operational condition is far more severe than usual, how can I say, the condition for workstation. Our workstation are so precious and so important, say they are placed in very good under good condition. Cooling is good. Also, they are not experiencing any kind of external mechanical disturbance. But think about our car. Inside your car, what happens? High temperature, severe mechanical disturbance, and so many unrealistic or unideal conditions for device operation. In that case, if you use the state-of-the-art device, they tend to fail quite quickly. So in this quite important industrial area, we intentionally use old time technology because they survived from the test of time. So they are proven that although they are not super fast and they are not, how can I say, most powerful, but it is guaranteed that actually they work. Even when we torture them, they can still survive from the severe, harsh environment. So nowadays, even nowadays, we have tons of planar MOSFETs actually being used in important applications. So in that case, maybe still we can have some use of these techniques. Okay, so that was the first step of our main contents. One was substrate bias. Simply speaking, when we have higher back bias condition, threshold voltage can be controlled, can be actually increased in the case of N MOSFET, and that can be used to reduce the leakage current. That was a short summary of our previous lecture contents. And now let's move to the next part called as mobility. And let's have a look at our previous equation. Oh, the number is quite low, 3.8. We have seen this number once previously, and what we have done was at a certain position at a channel, we must make the vertical integration to calculate the current density. And at that time, we assume that mobility, electron mobility, is a function of a position x, y. However, by taking the average quantity, so we can just pull it out of this vertical integration. So simply speaking, let's think about this one. This is a channel direction, this is a y direction, and this is a vertical direction, x direction, and we are now talking about this one slab. And here and there, and there, even for given y value, depending on the vertical depths, we can have different mobility values. For example, usually we have a very low mobility and relatively small lower mobility and high mobility and high mobility. Mobility can be a position dependent quantity. However, what we have done by this effective mobility is just to we make an average of mobility felt by our electron gas. So I mean that like this. Let's just say that this is vertical position and this is mobility function of our position, and let's just say, let me just draw in this way. Yes, this is happen to be, let's assume that this is happen to be the mobility of your device. Then my question is, from this one, how can you get your average mobility? Then maybe the first attempt you can do is, okay, so it's not that difficult. Let's just say the end of our system and just to make an integration and divide that integration by the depth of our system. Then we will have certain average value. That value will be, for example, given as average mobility. That can be your first choice. So are you with me? So let me just write down what we have done in more formal way. What I have done is like this. Just to make an integration from 0 to xi, so let's say that this is xi, and integrate mobility. After that, just to divided by depth of our integration. That was what I have done. So in this case, this point and that point, they are weighted in a same way. So if we increase mobility a little bit, and if we increase mobility a little bit, they are affecting to our average value in a same way. So let me just do a little bit manipulation. Here we have x sub I, then x sub I can be expressed as just integration of number 1 over our simulation or our analysis domain. So are you with me? So in this case we will have x sub I. This is the way we get this average mobility. The reason why I'm talking about this quite weird value is this is not our effective mobility. No, our effective mobility is given as the form shown here, and please make a comparison between our effective mobility and mere average mobility. What is the difference? In this mere average, I just make an integration of our mobility and divide it by its length scale. But when we talk about effective mobility, first of all, this integration is not just integrating electron density, also electron mobility. Instead, they are calculated product between mobility and electron density. Then, of course, then it doesn't give us a mobility related quantity. It will give us mobility times electron related quantity. So this electron related part should be kicked out to calculate mobility related one. So that's the reason why here in this lower part, in this fraction, so we just divide the integrated electron density. Please note that now here we have a certain integration of mu times n, and in below we have integration of electron. So when you make a normalization between them, we will get a quantity solely dependent on mobility. So what is that important? So now think about this one. Now say that our electrons are located, now I will just assume in this way. Our electrons are just shaped in this way. This is shape of our electron. Then if we apply effective mobility, then what happens to this effective mobility? Effective mobility will then, if we have such kind of electron distribution here in a purple line, then effective mobility will be just simply given as this value. That will be effective mobility. Because here we have n as a weighting factor, so if you have high electron density, then that part actually determines the integration. So when we make a vote for example, presidential election, everybody has one weighting factor, uniform weighting factor. But previously in Greek time, actually depending on wealth, somebody has more voting right and someone had no voting right. So then what happens? The election was highly biased to the rich guys. Quite similarly, if we have the weighting factor corresponding to the electron density, then this average value is actually highly biased to the position of highly populated part, densely electron populated part. This part will actually determine the effective mobility. So are you with me? Not just taking mere integration. Effective mobility is the average mobility felt by electrons. So that is done by this weighting factor. So electrons are more or less located quite close to this silicon dioxide and silicon interface. So simply speaking, effective mobility is determined by this surface mobility, not this deep inside bulk mobility. You know, if we go to deep inside this substrate, then we will just have minority electron mobility. There is just electrons are at that time just a minority carrier, almost no electrons are found. Well, they have quite a high value in terms of mobility value itself, but never contribute to the effective mobility because there is no mobility at all, or no electron at all. So now this slide just asks one question. Then up to now we have assumed that mobility is a function of a position. Then why actually mobility is a function of a position? Point is, now let's say that this is the given fixed y position, and we assume that depending on vertical direction, we have different mobility values. For example, when you go to quite close to the interface, we have a low mobility, and if we go to deep inside the substrate, we have a relatively high mobility. But why we assume in such a way? Why this surface part has especially lower mobility? That is my question. So simple answer is additional scattering mechanisms are located and happening nearby this surface part. One good example is like this. Silicon dioxide and silicon, here we have an interface, and we assume that electrons are found just nearby this interface, just a few angstrom or nanometer away from this silicon dioxide silicon interface. But in our ideal situation, this interface is atomically flat. But in reality, if you just measure it by microscopy, then electron microscopy, then actually you can find that there is certain roughness of your interface. It means that up to this point, we have a certain silicon, and the next position, up to this point, we have a silicon, and up to this point, once again we have a silicon, and now we have silicon in that way. This is one step of a silicon lattice, and also one step of a silicon lattice. And of course, beyond this point, we have, of course, beyond here, we have amorphous silicon dioxide. So silicon is a crystalline material. So when we have a look at it, using electron microscope, they are regularly placed, so they look quite beautiful. But this beautiful shape is not located in a quite flat way. They can have a certain up and down in this plane, so electron can feel like this. Oh, I wanted to move this path called as inversion layer, and it's like a highway. Good. However, in reality, this is the electron, but the way was not that smooth. The way was sometimes a little bit widened, and sometimes there is some hiccup. So this is actual load felt by our electrons. So that makes, of course, this is quite a rough and inaccurate description about this phenomena, but just please understand. So if we make an analogy, so this load, especially the interface between silicon dioxide and silicon, is not smooth enough. They are rough. So that's the reason why if our electrons are moving quite close to this silicon dioxide interface, they feel additional scattering. So compared with the electrons moving in this position, the electron moving in this position will be more frequently scattered by additional scattering mechanisms. So that's the reason why we believe that mobility at this point is much lower than that point. So that is the origin of a position dependency. Okay, time is up, so I will stop here, and in this Wednesday we will continue the discussion about effective mobility, and we will go to the short channel effect.